Okay, good afternoon, everybody. I'm Leonardo Baldi. I'm assistant professor in the Department of Mechanical Engineering, University of Maryland, College Park. And I want to welcome everybody to today's sessions of Future Leaders in Robotics and AI, Celebrating Diversity and Innovation Seminar Series. And this is part of the University of Maryland and Microsoft Robotics and Diversity Initiative, and it is sponsored by Microsoft DC Metro Engineering site. So today we have two invited speakers. I'll be talking for 30 minutes, about 20 minutes each plus questions. So the first speaker will be Angeline Aguinaldo, and she will be talking about a category theoretic approach to planning in a complex world. So Angeline, she's a computer science PhD student at University of Maryland, College Park. And the research interests lie at the intersection of knowledge representation, AI planning, and category theory. And she's also an AI researcher at the Johns Hopkins University Applied Physics Laboratory. So, Angeline, I'm afraid the floor is yours.
Okay. Let's see here. All right. You got my screen? Okay. Well, thank you for that introduction and for the invitation to speak at the seminar. As Eleanor said, my name is Angeline Aguinaldo, and I'll be talking today about a category theoretic approach to planning in a complex world. Now, when we talk about planning in robotics, a few things may come to mind given your background. So you might be wondering what type of planning will be discussed during this talk. So I just wanted to make that distinction. Task planning and motion planning are two types of planning relevant for embodied systems, and task planning is responsible for planning out a set of steps across a long horizon in order to achieve some overall objective. So for example, if you wanted to plan out the task of loading a machine with a part, then we might need to provide the high-level steps of opening the door, picking up the part, placing it in the machine, and closing the door. Motion planning, on the other hand, is concerned with determining what instructions should be given to a robot to actuate its joints in order to realize a path in the physical world. Now, both are important and necessary components to robotic planning, but today I'll be talking to you about task planning specifically. So task planning in robotics is concerned with identifying a discrete set of actions that transform the current world state into some desired world state. And the three components to planning are the world, the actions, and the planner. And in this example world state, it's a world state depicting a kitchen that has maybe a loaf of bread and a head of lettuce both on the countertop, and there's also a stool in front of the countertop. So given this kitchen world, we might want to specify a finite set of actions that we can execute to achieve some future goals. So in this kitchen world, we might want to be able to open objects or close objects or slice objects or pick up objects. And each one of these discrete actions takes a world state and updates it to produce a new world state that reflects how we would want that action to affect the world. Then the planner is responsible for arranging these actions in a way that transfer us from our initial state to a desired state or our goal state. And so in this case, if we have a planning problem, we can say that the initial state says that there are sandwich ingredients on the countertop, and the goal state is that there's a tomato and lettuce sandwich on the countertop. So given all these components, we might want to ask some questions like, well, how do we represent the world in planning? Or how do we represent actions? Or how do we represent how actions update the world? Now, if you're from the field of automated planning, you might find these questions interesting because a lot of good research in the field is focused around improving the performance of planners. And what I mean by that is that if we consider the role of a planner as finding a path between two states in a state transition system or a plan graph, then the planner performance is concerned with designing algorithms that can find the best path as fast as possible. But I think that there's also another interesting class of problems to consider, which is how do we leverage automated planning to produce effective plans? And what I deem to be effective plans are ones that address these open problems of how to handle complex world states, how do we transfer actions and plans between domains, and how should we manage implicit effects during the planning process. And I think these problems ultimately pertain to the representation underlying the planner and not necessarily the planning algorithm itself. So let me provide just a quick background on the classical view of planning. If we look at the origins of automated planning, we'll find that much of the field stemmed from the automated theorem proving community, and which is why that much of the underlying formalisms are based around first order logic and propositional logic. So the world state in a classical view can be represented as a conjunction of predicates that can ultimately have true or false values. Now, in order to handle actions in the classical view, we have to include some additional concepts, such as preconditions and effects, which are not inherent to the logical formalisms. And here, preconditions are conjunctions of facts that must be true in order for the action to be applied. And effects are conjunction of facts that must be true in the world after the action has been applied. And in this setting, the way that we would update the world is by leaving our first order logic formalism and moving to sets and using set operations to add and subtract facts about the world. So we argue that the classical representation is not equipped to handle these open problems because it lacks a formal semantics that unifies the world state, the action, and action updates. So there's a number of modern approaches that aim to address these problems individually. And I'll only go over one example because it's relevant for the approach in the talk. So if we want to address the problem of handling complex world states in robotics, we might want to use a formalism like scene graphs because they've shown to be effective in computer vision for capturing the objects and their relationships within a given scene. And they also align these instances of objects to a type class hierarchy or an ontology. However, approaches that use scene graphs in planning typically translate the facts within the scene graphs to the classical representation. And so they're still in a way subject to the same limitations as in the classical setting. The other examples are useful for addressing these open problems in isolation, but there is still more work to be done to consider solutions to all of these problems within a unified framework. So I'm hoping that my research contributions can address these open problems by providing a unified and formal semantics for planning based on category theory. So in this talk, I will discuss how we use a structure called CSET to represent world states as scene graphs, and how we can view the world state updates as a generalized form of graph rewriting that preserves composition. And at the end, I'll touch briefly on how we might transfer actions between domains by identifying isomorphisms. So now I will go through our approach using an example, specifically the example that I showed in the beginning about the kitchen world that demonstrates our proposed framework. So let's consider the example from the beginning where we observed that there was a loaf of bread and a head of lettuce and a tomato on the countertop. We also saw that there was a knife and a bowl and there was a stool in front of the countertop. Well, in this case, we can say that the countertop is behind the stool. And so for all these observations, let's imagine a perceptual system capable of doing scene graph generation constructed this scene graph in the form of a typed graph. And a typed graph is just a graph whose nodes and edges are assigned types from a fixed set of types. So given this type graph, we can probably agree that this is a reasonable candidate of a scene graph for this scene. So now that because it's a typed graph, we might want to consider the types and instances of the graph separately. And we want to make sure that we capture the original mapping between the types and their instances using these blue dotted lines here. So what you can see is that on the left, it's just the types and the relationships between types, which together we can call our ontology. And on the right, we have some instances and some arrows that seem to have analogies to the arrows on the left. And I've chosen to represent the instances as sets. And because we had initially a boring scene, there was only one element of each type. So all of these sets are singleton sets. So now that I have a bunch of sets that represent instances like a single tomato and a single head of lettuce and a knife, in theory, I could have also chosen different sets as the target for a variety of these types. So for the tomato type, I could have assigned it to a set of 2 tomatoes, or a set consisting of an olive or a bicycle or something else other than a tomato, and those being all the target of this tomato type. But instead, I chose 1 tomato because that represents the semantics of the scene. I say that because that means that the sets that I've chosen live in the space of all possible sets, and my assignment of blue arrows chose these as special ones from this space. And then let's say the arrows on the right between the sets also represent set function maps. And in this case, the mapping between sets is trivial because they're all singleton sets. So now going back to what I had described as being the left and the right, on the left, like I said, we have some types and some relationships between types depicted as arrows. And to the right, we have some sets and we have some set function maps. So but by me describing what the nodes and edges mean on both sides, we've almost arrived at a complete definition of something called a category, or 2 separate categories. One of them is just an ordinary category, free category, and a category of sets. So just to provide a formal definition, a category consists of a collection of objects, a collection of morphisms for every pair of objects, a composition operation, which says that if the source and target of 2 morphisms match, then there exists a new morphism called the composite morphism G circle F, or F composed with G. And lastly, for every object, there is an identity morphism that points every object to itself and satisfies some other rules like unitality laws. So we can look at these 2 graphs and consider them to be categories if we say that the arrows can be composed, and saying that we have identity morphisms that we've just omitted from the drawing. So now that we have these 2 categories, you can say we have these 2 categories, we can call the category on the left something called the syntax category, which provides us with a pattern that we can use to pick out objects in our semantic category set. And our assignment of one category to another, which is our blue dotted lines, can be then stated as a functor, which is a mapping of objects and morphisms between 2 categories that preserves composition. And preserving composition just means that if there is a composite morphism that exists in the source category, then there should be a corresponding composite morphism that exists between the target objects after we've applied the functor. So if we look back at our example, we can see that this assignment is a functor because there's a composite morphism between the lettuce and the sitting surface. And there's also a composite morphism that exists between the instances of the lettuce and the sitting surface. So we can call, now that we established that this is a functor, we can call each kind of assignment like this from a syntax category to a category of sets, something called a C-set functor. Now, also interestingly, is that C-set functors can exist in a category of their own called the category C-sets. And in this category, the objects are C-set functors and the morphisms are transformations between C-set functors. In this case, X is the C-set functor that we had defined in the previous slide. This is our original scene graph. And y is a C-set functor that has a new thing called bread slices, and these bread slices are part of the bread. And also apparently this bread has been sliced twice because there are two bread slices pointing to the bread. So an assignment between C-sets assigns each component, which is one of these blue dotted lines to the left, to a blue dotted line to the right. It also turns out that finding an assignment between two C-sets can be formulated as a typed constraint satisfaction problem. And a transformation alpha is considered a solution to the type CSP if it is something called natural, or if it satisfies properties of naturality. I won't go into the details of what natural means in this context, but it is essentially a natural transformation between two functors. Okay, so at this point, we've described what sets are and what it means to have arrows between them. So now we can ask the question of how we can use this, this representation of the world state to define actions in planning. Well, we can use what's called a double push-out rewriting rule that exists within the category C-set. Now, this takes the shape of two arrows pointing out of an object in the center, and the objects have been labeled I, O, and K for input, output, and keep. But we can also consider the input and output as our precondition and our effect of our actions. So our rule consists of three C-set functors. And let's say that our rule requires as a precondition the functor that assigns the type bread to an instance bread. And let's say our effect should have us arrive at having two bread slices be part of the bread. And the keep functor just tells us what objects should remain consistent between the precondition and the effect. So what we've constructed here is something that we can call our slicing bread rule. So now that we have a rule, we want to figure out how to induce a change in the world. So we determine that we have to first determine that the rule is applicable to our world state, and the applicability of an action in this scenario is determined by a special kind of morphism between two C-set functors called a monomorphism. And it's good to think of this as the generalization of an injective function in sets. So now that we've determined applicability, we can perform a double push-out square push-out routine, and we can arrive at Y as our new world state. And the nice thing about this is because we demand that the properties of a functor hold, this means any compositional relationship that existed in the source remains in the target category. And also because we're working in categories, this means we also have a compositional relationships between the bread slices being part of the bread loaf and the bread loaf being on the countertop. So there exists this composite morphism that says that bread slices are also on the countertop. And we didn't have to explicitly state that in our rule. And double push-out rewriting is a generalization of traditional graph rewriting algorithms with these added benefits of natively considering typing relations and considering these compositional path equations as constraints. So this representation still does not impact, this does not impact the way we might consider a planning problem as finding a solution through a planning graph or state transition system. So that means that we can implement existing search algorithms to adapt to the language of C-sets and DPO rewriting. So on this slide, I'm just illustrating some pseudocode and a search graph for a forward planning algorithm with backtracking. And in this algorithm, we also decided to incorporate some heuristics, such as a rule limit, to limit the amount of times you might want to apply a rule, like slicing bread, for example. We don't want to slice bread an infinite amount of times, so we can use the rule limit heuristics to determine whether or not that rule should be considered applied an infinite amount of times. A deeper explanation for this algorithm can be found on the blog post here on the bottom on the Algebraic Julia blog. So for future work, I'd like to evaluate this representation against other planning methods based on scene graphs, and then compare those plan qualities. And in order to do this, I'd like to implement a planning package within the algebraic Julia ecosystem. Here, I'd be able to leverage the existing C-set structure and DPO rewriting routines that already exist within CATLab Julia. Barring this implementation, there's a number of directions that this approach could take us. So as one example, one approach that this might help us find is finding analogies in planning. Because we've abstracted domains into this topological setting and then further separated out syntax and semantics, we can consider that transferring actions between domains is finding an isomorphism between a new planning domain and the rewrite rule. Another example that we might consider is that if we think of our rewrite rules as simply update rules to a structured knowledge base, we can envision scenarios where a human or another machine might want to update our knowledge base and then dispatch a new planner to begin from this new state. This would not require us to rewrite the domain in order to suit the new information we obtained. And also this would not require rerunning the planner offline because we didn't have to take it down to reinstantiate the domain. So this might allow us to be a little more amenable to solutions like online planning. And lastly, an action being applicable to the scene may be conceptually the same as saying an action is afforded by a scene. So being able to discuss these relationships formally may give us access to definition of scene affordance relations that is based in formal theory. So if you're interested in any of these projects or having a deeper conversation about what I talked about, feel free to contact me at this email address. Thank you for listening. I'm happy to answer any questions.
Thank you, Angeline, for the very interesting talk. So for the audience, if you have any questions, please feel free to write it in the chat. We have a few minutes for questions before we're going to move to the next speaker. So in the meantime, I can ask a question. So referring to, if we can go back to slide 10, right? To
slide, I'm sorry, what was that, 10?
Yeah, number 10. Yeah.
Mm-hmm.
So we're talking about the scene graph. So I was wondering, what if, for instance, the tomato would be on top of the bread? Would that be considered a composite morphism, or no, there are two separate objects? So would there be a rule between the two?
Yeah, so we could probably adapt this scene graph to include another relationship where tomato is on bread, including that as a type of relation that exists in our ontology. And then we would identify an instance of a tomato being on a bread on top of the bread with using this new type of relation that we've defined. So yeah, basically, if you wanted to extend the ontology to a different type, more types of relations that say objects can be on top of other objects, you can instantiate that in the syntax category and then just find or identify instances of that in your semantics category.
Thank you. Okay, we have a question. So can you please talk a little bit about how you would extend to continuous space planning?
Yeah, that's a very good question. And that was part of the reason why I made the distinction in the beginning between task planning and motion planning, because the task planning is concerned with discrete actions. This is a formalism that kind of treats, aligns with that model of treating these actions as being discrete. There may be extensions of this that would support continuous space planning, but as of right now, this is towards task planning.
Thank you.
Thanks for that question.
Any other questions? There is
yeah, that's
a follow-up question. Yeah. To kind of represent recursive concepts in category theory.
Yes, yeah, there are. There's a variety of structures that could be tailored to a concept of recursion. So it just depends on what would you like to get out of your structure. But one thing I can think about is operands, which kind of can capture this sort of hierarchical composition of processes being called from within other processes. But there are other options that you might need to consider depending on your application. But yeah, I think recursion is a reasonable request from category theory.
Thank you so much.
Mm-hmm.
So the speaker will also be available after the second talk for some short follow-up questions. If somebody from the audience would like to ask a few more questions.
I'll add for the interest that we are recording the seminars, and the videos will eventually be posted to the website robotics.umd.edu/futureleaders.
Thank you, Jens. Okay, I think in the interest of time, we can move on to the next speaker. We thank Angeline Aguinaldo again for the great talk.
Okay, thank you.